All right, as promised in this video, we're going to take a look at the derivative of the exponential function, specifically this one, e to the x. We'll look at other versions of exponential functions later on in this course of videos, but for now we're just going to focus on e to the x. So the first question is, what actually is the number e? That might seem like a silly question for some of us because we know in general kind of what e is, but what we're going to do is give an actual definition of it, and that definition is going to be based on a limit. From there, we'll be able to use that definition of e to be able to find the derivative of the exponential function e to the x. Just a quick note before we get too far into this video, there are lots of different ways of defining the number e. And depending on your definition of that, that might change things a little bit. What we're going to do is show that the derivative of the exponential function is itself. The derivative of e to the x is e to the x. That's going to be our big result. And so sometimes we might start with this as a definition and say, let's consider the function whose derivative is itself. And then we can work backwards and come up with a definition of e that way. What we're going to do is we're going to look at things that are a little bit more historically motivated. We're going to try and figure out where e comes from, and especially in our context that we've seen before, and we'll build forward to this derivative rule. So if you're looking up things elsewhere, you might find a whole bunch of different definitions of the number e. That is absolutely okay. All right, so again, what is this number? You might know a little bit about this from your high school math classes or something like that. Most of the time, what we do is we see this in compound interest. But in general, e is Euler's number. It's been a number that's shown up in history in a couple of different contexts, but we give credit to Euler for it, like so many other things in the realm of mathematics. We probably are familiar with it from compound interest versus continuously compound interest. So that's like a equals, and you have a whole bunch of different versions of this formula, but here's one of them. A equals P times 1 plus R over N raised to the NT, where P is your principal investment amount, R is your interest rate annually, N is the number of compounding periods per year, and T is the number of years that you invest this stuff. Or this continuous compound interest, this is our PE to the RT, where everything stands for the same stuff, and now E is this constant. E is an irrational and transcendental number. It's a lot like pi in that respect. All the nice, cool properties of pi that we have and we love are the same for e. It's got this nice decimal expansion that never ends and never repeats, and it has all of the same kinds of cool things about the number itself because it has these same two properties. But again, what we'll know is that we need a formal definition of e. What you might already know is that e is something around 2.72-ish, just like pi is around 3.14-ish. So we have this nice approximation of it, but we want a formal definition. So let's start with this distinction between compound interest and continuously compounded interest. What is continuously compounded interest? Well, that means that we're compounding all of the time. Okay, so let's think about what that means in this context here. What that means is that we don't have any distinction between compounding periods. It's not like we compound interest on 1 week and then we wait and then we compound interest on the next week, where n would be equal to like 52 weeks in the year, compound interest every week. What we're saying is that we never stop compounding interest. And so what we're looking at is a limit as n goes to infinity, where we have an infinite number of compounding periods per year. And that's one of the contexts where e came up historically. And so if you do a little bit of work with that, you can define e this way. And this looks relatively familiar, right? This has a similar form to this compound interest. We're leaving out the t and the r, but those are put in over here. So you can kind of see that this is connected. One of the definitions of e is that it's this limit as n goes to infinity of 1 plus 1 over n raised to the n. Cool. Let's think about what this actually means. It's 1 plus some infinitely small value, right? Because we know 1 over n is going to approach 0 as n goes to infinity. But we're raising that thing that's a tiny, tiny, tiny bit bigger than 1 to an infinite power. And we're saying that this is approximately 2.72-ish. It's kind of weird, right? What I'm going to do is a little change of variables. I'm going to say let's consider the case where h is equal to 1 over n. What you're going to notice is that we're just going to flip this upside down, and then if n goes to infinity, we can hopefully see that h is going to go to 0. So let's just write our limit that way. Again, this is with h equal to 1 over n. And so this is really 1 over h, this is really h, and then if n is going to infinity, again, h goes to 0. So this is an alternate definition of the number e. It's exactly the same thing, we're just using a reciprocal to change the limit structure. That's going to be a little bit more helpful for us. All right, so that's what e is. You might have seen one or both of these limits in your homework stuff because normally we'll have people approximate these limits when we're learning about limits and notice, oh yeah, this looks like this weird number that I've seen before, 2.7-ish. Let's go ahead and differentiate the exponential function using this limit rule, this limit definition of e. So we're going to use this one specifically, the 1 plus h raised to the 1 over h. You might recognize that I'm using h's here because it's going to match really nicely with our limit definition of the derivative. You can also see why I wanted to change the limit from something going to infinity to something going to 0. Our limit definition of the derivative has h going to 0. So that's my motivation. All right, so we start up. This is our f of x plus h minus f of x. And notice just by the rules of exponents, we can go ahead and split this thing up, right? We know that like x squared times x cubed is really x to the 5, and that's 2 plus 3. So we're just going backwards here. We're taking this sum in the exponent and breaking it up into a product of exponentials. Once we do that, you can notice that e to the x is a common factor here. And so what we have is we factor out this e to the x, and we're left with e to the h minus 1 over h. This is the pretty standard way of approaching this proof. Sometimes people will just kind of figure out what this limit is by approximating it numerically. But what we want to do is notice that we can break this up into a product of limits. Notice that this doesn't have any h's on it. So this e to the x part, as h goes to 0, it just stays e to the x. And what we really are going to focus on is this limit. Again, there are multiple ways of approaching this proof. Sometimes people will start with the definition of e being the number that makes this limit be what we want it to be 1 here. What we're going to do is show that with our definition of e, this limit actually is 1. So we need to figure out what's this limit where e is this 1 plus h raised to the 1 over h. So we're going to take this thing and we're going to chuck it right in here. Notice we already have a limit as h goes to 0, so I'm going to leave that off for now, and we're just going to see the 1 plus h thing go into place. So there it is. 1 plus h raised to the 1 over h, all raised to the h. All right, notice when we raise an exponent to an exponent, these things multiplied together. So this is really 1 plus h to the 1, but that means we don't really need these parentheses. And now we've got these nice like terms that we can combine. We have a 1 minus 1. That's clearly 0. So we have h over h. No matter what h is, as long as it's not 0, h over h is 1. And guess what? We approach 0, but we never actually equal 0. So this is really a limit of 1. And so just like we wanted, that limit is 1. Okay, so let's go back to our derivative of the exponential function that we were working on. We were right here, right? And we said, oh, we need to figure out what this thing is. Well, let's just put 1 in place of that. Now, this is e to the x times 1, so it's e to the x. And so here's our big result. The derivative of the exponential function e to the x is itself. This is the only non-trivial function that does this. What I mean by non-trivial is I mean like it's not a silly version of this. There's one other function that I can think of off the top of my head that does this. The derivative of 0 is 0. 0 is a constant function. And we found in our last video that the derivatives of constants are 0. That's not a very interesting case. That's what we mean by non-trivial. This is not a really interesting function. This is an actual interesting function, and it's the derivative of itself. That's pretty cool. So our exponential function is really interesting, but also it's a pretty easy derivative rule to memorize because we just get to leave it alone. In our next video, we're going to start taking a look at a couple of examples where we start combining these function types together because we have a couple of different functions now and some operations that we're aware of. So hang in there. Let's take a look at some examples and we'll start getting pretty familiar with how this goes.